Well, good morning, everyone. Again, so nice to have you with us this morning. I'm Professor Bob White. This is the 70th Senior Engineering Design Conference here at Western Michigan University. It's 35 years worth of Senior Engineering Design Conferences. They've all been wonderful. I can tell you, I've been to them all. So we're so glad that you're here with us this morning. I think you'll find the presentations very impressive. It's very exciting and fulfilling to watch these students, these young people, come to us as somewhat apprehensive freshmen, grow into mature, confident, capable seniors and young engineers. It's just very rewarding as faculty members to see that. We have some special recognition we want to give for people that are with us. Not always possible for people to be here, but we have some people online, and we welcome our online audience as well. And we have Diane and William Franchek, the parents of Noah. So very pleased that you're here with us. We also have several faculty members that are with us. We're very pleased that they're with us as well. We have a very special faculty member with us this morning that I want to recognize, and that is Professor Frank Wolf. Frank Wolf is the former chair of the Department of Industrial Engineering here at Western Michigan University. I kind of like to think of him as the chair that brought us into what I would call the modern era here at Western Michigan University. He was the chair that we first received our ABET accreditation, which at that point was ZCPD. And he was very instrumental in hiring several of us as faculty members, including myself. So I thank Frank for the opportunity to work here, and we're very pleased that you could be here, Frank. Thanks for joining us.
Thank you, Bob.
Yeah. The presentation this morning is Analysis and Improvement of Industrial Door Production with Noah Franchek, Anthony Kemp, and Josh Morris.
All right, so hello everyone. Our group is working on an analysis and improvement of industrial door production. We're working with Senneca Holdings. The group consists of Joshua Morris, Noah Franchek, and me, Anthony Kemp. Our sponsors consist of Dr. Azim Bouchard, Dr. Bob White, and Professor Dana Hammond. And then we also have our industry sponsors, John Early, the Director of Engineering, who's in the back, and also Josh Gray, who's the Assembly Supervisor in the area that we're working in. So for today's presentation, we're going to start off with Senneca's background, then we're going to move on to project objectives and overview. After that, we'll move on to the project plan, followed by data collection and analysis of the areas that we covered. After that, we'll move on to our recommendations and then any questions that you guys have. So to start off, Senneca was founded in 1932. They are part of the specialty door industry. That means that their doors are everywhere from in restaurants and grocery stores, and that can be when you enter a kitchen of a restaurant or even the main door of that restaurant, or it could be in the back of the grocery store. It can also be anywhere down to the doors that are provided to universities, or even hangar bay doors for aircraft hangars. We're currently working at their Portage, Michigan location for this project. And what we're working on is their shipping bay roll-up doors. These can consist of different materials, but the main ones are vinyl or mesh material. So those have a variety of opening and closing mechanisms for the doors. These can be a spring-loaded opening or closing mechanism, an internal motor or an external motor, for example. The sizes range anywhere from 36 inches by 36 inches to 168 inches by 168 inches, although you can custom order sizes over 200 inches by 200 inches. Currently, they're making about 7.5 doors per day in their process. Okay, so to go over the actual assembly process itself, you'd start off with whatever material the door is made of. You would cut that over at the cutting table. Then you would take it over to the heat seal, where it would meet a piece of heater, like so. And the heater would be fed into the material. It's a bit sticky, so it takes a bit. And then it would be lined up properly, and then it would be ran through the heat seal down in place, so that way it's stuck together. And it would do this for however long it needs to go. Typically, it would be multiple presses for a door. It would be flipped and then pressed again for the other side as well. Then this material would come back to the cutting table, where someone from the assembly table would come over, pick it up, and assemble it. And it would look something like this. Now, this would use a wind bar here. This would be fed in to the actual door, and it would allow it to line up. So this would be the actual height of one of the panels, and it would be multiple panels stacked up, and it would go out for however long the width is needed to be. When you get to the bottom portion, you would take a bottom bar, and you would feed it in at the same process that you do with the normal heater. like so. And then also the bottom bar would have a specific end heater go on the bottom to make sure that it's nice and sealed. And then the last part would take these breakaway tabs and they would go into the side of the door. And this would use the guide rails on the side when the door opens and closes to actually feed it in properly. At the same time as all that's going on, you'd be over at the fabricating tables where the actual cutting and drilling of the opening and closing mechanisms would be going on. Specifically the cutting at fabricating table 2 and then typically the drilling over at fabricating table 1. When this is all done, the two different processes will meet up packaging and they will be packaged together and then shipped out of the system.
So from that assembly process that Anthony just explained, we come to the challenge of throughput. So Senneca came to us with this project because they're currently facing a 2 to 4 month lead time with their screen doors, and they're really struggling to keep up with demand that has been increasing over the past few years. So Senneca came to us and wanted us to create a one-piece flow in the production and have everything run a little more smoothly and have there be less wait times between stations. So to kind of sum that up to a challenge statement, we want to design an approach to reduce bottlenecks and inventory levels, increase throughput, and help meet a one-piece flow system. And to kind of break that down with our project objectives, we have 5 of them. We want to improve the product flow. We also want to improve the workstation efficiency of the department, and we also want to do some facility layout changes. And on top of improving those things, we want to reduce the inventory levels, and we also want to reduce machine downtime and maintenance costs of the bottleneck. So to kind of organize our whole entire project, we used the Six Sigma problem-solving approach called DMAIC. And DMAIC is a data-driven tool used for optimizing and maintaining business processes. And DMAIC stands for Define, Measure, Analyze, Improve, and Control. And what we did for this is we initially defined our problem through observations and interviews with current employees and management. And from there, we were able to find the correct tools to measure those problems. And then we went into analyzing those measurements and collecting data. And from there, we were able to make improvements. And we want to do weekly follow-ups with Senneca to kind of control the improvements that we made. So the first step of DMAIC is defining the problem. So we have 3 main points that we want to talk about for this presentation. The first one being inventory levels. We found that there was an extreme amount of excess inventory at Senneca in the facility, and we also found out that, or saw that there were some racks that were unorganized. The second point is facility layout. There's some insufficient space and some things we want to move around. There are some lighting issues in the department, and we also want to do some workstation design changes. And finally, the biggest topic that we spent the most time with for this presentation for this project was the bottleneck downtime. We found the bottleneck to be the heat seal, and we'll go more in depth in that later, but the heat seal is a very complex machine that has been having electrical issues. So the first topic is inventory management. We found that there are over 5 racks of the vinyl rolls to make those screen doors, as you can see in this picture, and that really takes up a lot of space. We also found that there were 53 years worth of the least used rolls, and there's a large variety of these different colors, or of these rolls with different colors and different sizes, so there's a lot of different options for the customer. And the common colors that are mostly bought by the customer is really scattered between the racks in the facility. So based off of a walkthrough we did in April, we found the most common colors really only took up 31% of the inventory space, and the most common colors that we've seen throughout the year working on this project were the blue, red, and gray screen doors. And that means around 500 out of the 700 square feet of inventory space were taken up by uncommon colors. So we think that if we can reduce these other colored doors a little bit, it can lead to better organization in the facility, and we can also move those more common colors to racks that are closer to the department that we're working with, so there's lower transportation time for the workers. And now Noah is going to go to our next topic, which is facility layout.
So for facility layout and workstation design, the first thing we did was interview employees and the supervisor judge. The first complaint that we got was the lighting in the department. As you can tell with the department is that it seemed pretty dull in there with the lighting. It was just some overhead lighting. So we went around to each workstation and we measured each workstation, each 4 corner. We averaged it out. We averaged it out to about 300 to 200 watts per workstation. And according to OSHA and ISHN, it's supposed to be around 500 to 750. So, and with precise work in the fabricating tables, with like precision drilling and sawing, it should be around 1,000. So here's the old lighting, as we can see, kind of just overhead lighting, and with this, it created a lot of shadows, which could lead to error, especially in those fabricating tables. So we brought this up to John, and in April 7th, they actually installed new lighting, which is some overhead aisle lighting that they put up. And it's with the new lighting, we measured it, and it came out to be 700, 800, even 900 bucks. But the one problem that we encountered again was the fabricating tables. The fabricating tables, they didn't get an overhead light for them, so a lot of the lighting was behind them. So it created even more intense shadows. So we're going to recommend getting a new light for those fabricating tables so there'd be less error with them. The next thing we want to talk about is the packaging table and the packaging table blockage. The packaging table, as we see right here, it kind of just goes into this walkway that we want, and it bleeds out with all the shipments, and then they'll have carts around that too. And with this walkway, we want to have forklifts and people going from department to department. So it really blocks it up. So we're going to recommend getting the fabricating tables and combining them into one table. And with that, we can bring down the assembly table, cutting table, and then the packaging table all down, and then it will stop bleeding into that walkway so we can have an increased flow for that walkway. And with this, there'll also be canceled walking between the two tables, because with that, we took time studies of it. There's just unnecessary walking between the two tables going from drilling. And then we talked to the lead fabricator there, Ryan, and he showed us this one workstation in a different department of the facility in the bottom right. It's something that we are going to recommend as a one work table there. We can have all in one for them. And then the third topic we want to go over, and the main topic, is the bottleneck, and that is the heat seal. As we said, they were struggling with throughput in the system and keeping up with the demand, and we noticed that the heat seal was kind of being that bottleneck that was slowing everything down. So with that, first of all, the heat seal is kind of like the foundation of this process, production process. Everybody kind of waits on it to happen, and it kind of just encounters the door. First off, the machine isn't made for the process that they're using it for, and then also the machine is very old and it has a lot of wear and tear on it. So with that, we talked to the in-house maintenance man, Bob, and Bob was saying that there's a lot of problems that they're encountering. It's wiring issues, circuit board issues, and just overheating and arcing. So with that, if Bob can't even fix it, they send it outsourced to another maintenance man, and that's with a supplier, which will cost more money and then also lead to greater downtime. And we estimated the downtime for the heat seal to be down for about 45 days a year.
So to kind of measure the performance of this heat seal, we used OEE calculations, which stands for Overall Equipment Effectiveness. And it's a standard industrial measurement that a lot of companies use. And what you do is you multiply the availability of the machine by the performance of the machine, and then by the quality of the machine. So to kind of go over a quick example so you guys know how it works, let's say a worker is at their workstation for 7 hours out of their 8-hour day, so 87.5%. When they're working, they perform at the 93rd percentile based on the speed and efficiency of getting their job done. And they also create 3 defects out of every 100 parts they make. So what you would do is you put all those percentages together and get your OEE calculation. So for the heat seal, we did just that, and we found that the major issues were the availability of the machine and the performance of the machine. And they were sitting at 81% and 80%. And that got us an overall equipment effectiveness of 64.15%. Now, when we did a little research into OEE calculations, we found out that 60% is typical for manufacturing industries. So we're at a typical level right now, but 85% is considered world-class. And based on how competitive markets are today, we want to move this process up to the world-class level.
So the first thing we did with the heat seal is that we started taking time studies of it. We took time studies for about 20 times, and we also did time studies for the shipment builds and also the drilling press. And with this in the center table, we broke it down for the heat seal per process. We took the averages of that, and then on the graph on the right, we have actual versus goal time. That is, what the goal time is some processes within the heat seal that we think can be a smaller amount of time due to a new machine, which leads us to my next slide, which we're going to recommend a new machine for Senneca. So the heat seal, as I said, is down for about 45 days a year. So in production, that's pretty not okay for us. So we want to look at the R-Flex and the R-Flex travel by Miller Weldmaster. As we asked John, he recommended Miller Weldmaster as they said, and they keep those machines in other parts of the facility. And we found the R-Flex travel would be the best one for us because it's almost a direct replacement of the machine they have, and it would just decrease that downtime for them.
So to be able to actually see how a new machine might perform and change the system, we need to design a process simulation. So the process simulation would recreate the system in a digital environment. It would show daily variability in the throughput via the time studies that we used. We used to identify the bottlenecks, such as the heat seal, and see how different changes would affect the system. So the current system in the simulation was the first thing that we built. Currently, we have it producing about 7.84 doors per day in the simulation, and that will be a 95% confidence that it's between 7.09 and 8.59 doors per day. This lines up really well with the 7.5 doors per day of current throughput that they have in the system. Then we moved on to the improved simulation. So for this, we merged fabricating and hit tables 1 and 2 together. This would allow us to bring everything in and clear up the aisleway. At the same time, we also introduced a new heat seal machine. We created a variety of different simulations for this. Some of the main ones are shown here. To go over them, the worst case scenario is that there is no speed increase from the new machine, and that it is purely a reduced unplanned downtime. For the most likely scenario, it was a slight increase to the actual sealing process, and a downtime or an unplanned downtime reduced to 10 days out of the year. The best case scenario was a variety of improvements to the actual speed itself in the system, or at the heat seal, and a 0 downtime at the machine. And then the 1 seal is a theoretical approach. We've not seen anything capable yet of producing this, but it would pretty much just do the entire heat sealing process in 1 push instead of having to do multiple pushes for the length, flip, and again. So these resulted in an 8% increase for the worst case scenario, an 18% increase for the most likely, a 23% for the best, and a 39% for that theoretical 1 seal process.
So based on that improved system that we created, we redid the OEE calculation, and we could see that the availability increased up to 95.8% from that 81% currently, and that's mostly due to reduced downtime with that new machine. We also saw performance increase a little bit, and that gave us a new overall equipment effectiveness measurement of 78.71%, which is a pretty big jump from that 64% we previously. So after all that, we kind of were able to do some financial analysis measurements. And the first one that we did was break-even of production. And break-even really, it compares the cost of the old process per door with the new process that we created. And we used this formula. We added the material, labor, and downtime costs per door. And then we also added the new machine costs for that improved setup. And we compared the two, put them up against each other, and found that our break-even point was at 1,436 doors. And from there, we're able to save around $93 for each door that is produced with that new machine and the new setup.
All right, so the next thing we did for the financial analysis was we actually introduced variability into the system. So we introduced the variability for 10,000 trials in each different scenario. So we varied things such as downtime, production loss during downtime, maintenance costs, and more. This resulted in the table that we see on the right, where the 5% is the 5% best case scenarios. The break-even average is the average number of doors that we would break even at. And the 95% is the 5% worst case scenarios for when we break even in our simulation. So to just quickly go over it, the most likely scenario came out to about 1,442 doors to break even. The worst case scenario on average was 2,236. And the best case scenario was 1,135 doors. Another thing to note on there is that even in the worst case of the worst case, the 95% worst case scenario, we were still breaking even after about 5,500 doors, which is about 4 years of production roughly, which means that it's a good idea to consider.
So to go over the recommendations for Senneca, we have short-term and long-term recommendations. For the short term, we want to just combine those fabricating tables to improve that walkway and for the forklifts. And we also want to add the additional lighting for that fabricating table or the fabricating tables, depending on which one they do first. And then for the long term, we want to recommend adding in that R-Flex machine, as we saw increased throughput into the system. And then we also want to evaluate the new processes. And with that, we want to start examining the door assembly. because with our simulation, we saw that the door assembly started becoming the new bottleneck within the simulation. So just to recap the whole project, John came to us and was struggling with the demand and the throughput of the system. So we broke it down into about 3 different topics, which was inventory levels, facility layout, and workstation design, and bottleneck downtime. For inventory levels, we want to reduce the less used roles, and that would just clear up space for them. And then for facility layout, workstation design, we want to rearrange that layout, like I just said. That would increase the flow, and we want to also increase the flex. And then with the bottleneck downtime, new machine introduced that R-Flex travel, which would save about $93 per door. And that concludes our presentation for today. Do we have any questions?
Anyone have any questions for the crew?
I thought it was really well organized. I enjoyed the presentation. Did you get a sense of what the cost is of what it means?
The cost of it?
Yeah.
The cost of the new machine was around, I think, $133,000 after like shipping and installation costs.
Great project, very well done. Is there anything that was out of scope in your project initially that in hindsight you were wishing was in scope?
I would probably say with the out of scope initially, I would say like the inventory levels. I wish we'd like to spend more time on that because that was like a problem that was introduced to us kind of like in March and April. So I wish we kind of could focus more on that.
Anyone else? Thank you very much.